is actually a director of ray tracing R&D at the Imagination Technology. He is an engineer and also entrepreneur. He worked for Apple before, and then he found a company named Plastic Graphic and worked on ray tracing technology. And the company be acquired by Imagination in 2010, and then he's keep work on that. And this technology will getting a big breakthrough very soon, so you will see many applications come out very soon. So let's welcome Luke Peterson.
Good afternoon. So it's a real honor for me to be here today. I'm really grateful for the opportunity to speak to you. As Simon said, I'm going to talk to you about ray tracing. Ray tracing, we think, at Imagination, has a lot of promise. It's not quite as life-saving as what Dr. Pandit just presented, but we think it's going to be pretty big nonetheless. So at Imagination, we've designed a new graphics processing unit that dramatically improves the efficiency with which you can do ray tracing. And I'll be explaining how that works. And along the way, I have to explain how ray tracing itself works and why it's not just a game changer for games, but we think a game changer for more than that. So, so let me get going. So there's a picture of a car. This was created with our technology. And the point here is the ray tracing is already used today. It's been around since the 1980s. It's not a new technology. So it's used in industries like automotive for doing pre-visualization. Well before a product ever comes off of the production. Well before a physical prototype is ever created. Companies will do pre-visualizations in order to figure out, cars are shiny. You need to know exactly how the light's going to hit the car, see how it's going to work. You need to know what parts of the car are shadowing other parts of the car. That's not just true of cars. That's true of every product. So, so ray tracing is already used throughout many industries, pretty much anybody building something physical, in order to get an idea of how it's going to, what that product's going to look like before they, it saves millions of dollars in prototyping. And here's another car. This was probably also created with our technology, although this one I can't prove. I just know they're our customer. But this, again, before anything rolls off the production line, all the advertising assets are created ahead of time. If you ever think that products in ads look a little bit too good to be real, well, they are too good to be real. They're not real. So yeah, ray tracing is used already today in these niche, very important but low volume applications. But there's a much bigger application of graphics out there, and that's the interactive application. User interfaces and games. Basically, anything that has to hit a certain frame rate has to achieve a certain speed. So while ray tracing is really great for pre-visualization, it's good for architecture is a big one. Show me a picture of this building in situ, where it's going to be built, so you can see. I heard a story about a building they built in London. I think they had another one in Las Vegas that was burning people because it was a big reflector dish that was focusing the light of the sun onto the poor people at the pool. And yeah, they clearly didn't do adequate architectural pre-visualization. So ray tracing is used, but the vast majority of the volume use cases don't use ray tracing today. The reason for that is there's another technique called rasterization, which is a lot lighter weight, and that's what's used in games. It's so it's kind of like you have the when you need accuracy and quality, you use ray tracing. When you need speed and interactivity, you use rasterization. So the point of what we're doing at Imagination is we think we can bring ray tracing into those areas that are traditionally it was not suitable for. We think through the efficiency improvements. So, I'll go into that, but let me just back up a bit. What ray tracing is? Ray tracing is the basis for a physically accurate mathematical model for the behavior of the physics of light. So ray tracing, again, one of the use cases is Hollywood. Well, not all. The vast majority of special effects in Hollywood are rendered using ray trace rendering. So there's a hypothesis called the Uncanny Valley. Games today already look really, really good, but the better something looks, the more real something looks, the more, and specifically, the more it approaches looking like a real life person, the more the user, the viewer, or the person can relate to it, can connect with it at an emotional level. So, you know, it's built into us, it's hardwired into us. But the Uncanny Valley hypothesis says that once it gets too real, but isn't perfect, once it gets, you know, to that 90% mark, then instead of connecting with it, we're afraid of it. We're repulsed by it. One guess as to why that is because you know, you can see right at the bottom of the Uncanny Valley are corpses, and well, if people like to hang around with dead people, it can be really bad for your health, and so people who did that probably didn't get a chance to become our ancestors. So it makes sense that we wouldn't really, that we would be afraid of things that don't quite look real, like dead bodies. So yeah, it's pretty important to stay away from, to avoid that Uncanny Valley. Many things contribute to what we perceive as being real, to what we can relate to. One of those things is, you know, obviously there's how it moves. There's, you know, there's its facial expressions. Can you see the emotions in its face? But another one is the subtle interactions of light. And that's what ray tracing is going to solve. Or, well, what ray tracing does solve. So, this is a screenshot, a real screenshot from a real video game that just came out last year. It's kind of terrifying. And I don't think that's what the game developers were going for. So this is a perfect example of the Uncanny Valley in action. So this is the stuff of nightmares. And it's an example of computer-generated imagery falling right smack into the middle of the Uncanny Valley. Here's another screenshot this time from a movie in 1995. If you ask me, he's in the Uncanny Valley as well. So, you know, his eyes, you know, he's pretty terrifying as well. His eyes look like they're painted. His skin looks like they're plastic, like it's plastic. I mean, he looks like a toy. And the audiences would never connect to this guy. If there was a movie made where he was the protagonist, like, that movie would be a flop. So what's the solution? Well, make the movie about toys and make him the bad guy. So that was the first. This was the first feature-length, fully computer-generated movie. Came out in 1995. So where have we come in the last 20 years? Well, Hollywood has overcome the Uncanny Valley. I have never embraced a chimpanzee. I've not really even spent any time looking a chimpanzee in the eyes. But this chimp looks really, I can connect with this chimp at an emotional level. I have no problem believing this chimp. So it is possible to get out of the Uncanny Valley. And it's possible using ray trace rendering. So how does ray trace rendering work? It's actually really, really simple. It's a very simple idea, and like I said, it's been around since 1980. You basically, it's all about line segments. You just, you know, in this case, you take the line segment, doesn't show up so well in the projector, but you start the line segment at the sun, you pick a random direction, and you move along that line segment until you hit something, in this case, a green box. Well, the mathematical model for the green surface says that it's going to absorb all the wavelengths of that light except for the green, and as a result, then you do it again. You pick another direction, and you pick another line, and you move away, and that ray then is carrying the information that green light is moving in this direction. And eventually that ray is going to find its way to a camera. And then you have a mathematical model for the lens in which you take the information about the ray and you calculate, using the lens model, you figure out what pixel is green, and that you contribute whatever green light came from that ray into that pixel. And that's ray tracing. That's all there is to it. Pretty simple. But to do it right, to get a good image, you need to do this literally millions, well, many, many millions of times. And if you don't do it enough, if you don't have enough rays to find the camera, if not enough of your rays find the camera, you get an effect that's perfectly analogous to an underexposed photograph, because it is an underexposed photograph. An underexposed photograph is not enough light making it through the aperture onto the film. Ray tracing, you have exactly the same problem. So if you don't use enough rays, you can get an underexposed image. Yeah, so all that grain there, or as we've talked about it in image processing terms, it's image noise. That's the result. Now, it would be a little bit wasteful, as you can see, to trace all the rays from the light to the camera, because the vast majority of them don't hit the camera at all, and as a result, they don't mean anything. They don't contribute anything to the picture. So there's an optimization we can do that we can trace the rays backwards. So it turns out light is fairly bidirectional. The math of light propagation and scattering is fairly complementary. So you can do a lot better by working backwards from the camera to the light source than you can from working from the light source to the camera. So that's basically ray tracing. It's not a very complicated algorithm at all, but there's a lot of reasons why it hasn't been fast enough for anything except really slow offline processes. So I want to go into a little bit about how a GPU works. So, and to do that, I think I need to go through the history of how we came to have these GPUs. So in the beginning, GPUs were dedicated fixed function silicon units. They basically transformed data coming in through the pipeline. So in the front of the pipeline, you had three-dimensional vertices, and as basically it goes through these stages. The first stage is each one of these vertices undergoes a transformation based on the viewport. So it gets transformed with respect to the projection view, the place where it's the position of the viewer. And then it gets projected, which is to say flattened from 3 dimensions into 2 dimensions. So at that point, you have instead of having 3-dimensional points in space, you have 2-dimensional points on a screen. The next step then is rasterization, also called scan conversion. Basically, you just go each row of pixels. When you walk along each row of pixels, and you work out every fragment, every pixel that the triangle overlaps. They call those fragments. Those are pieces of triangles that overlap pixels. Then, for each one of those fragments, you need to figure out what color it is. And that involves a little bit of performing a basically shading operation, which could be usually you are aware of the light, and then you do some calculations to figure out how much of the light is reachable by basically how much the light impacts that pixel, usually or that fragment, usually depending on the fragment's orientation. Usually just is as simple as, or in the old days of computer graphics, it was as simple as a cosine. And then finally there's blending. So once you have a color worked out for each fragment, you blend that into the pixel. So so the pixel contains all the information for all the triangles, all the colors for all the triangles that were drawn to that. So pretty simple. And these were originally these fixed function bits of hardware that, you know, they started to show up in the 1980s, and they really had a heyday in the 1990s. And around about 2002, the architectures started to evolve. Not that they weren't evolving before that, but they really started to evolve then with the addition of programmability. So programmability first showed up as this vertex shading part of the pipe, the projection part of the pipeline being replaced by what's known as vertex shading. The idea there is that you have a short program that you can run on each and every input vertex. So it's, at first it was just a few instructions. Ultimately, it became its capabilities grew. And then not long after that, the shading part of the pipeline became programmable as well. So at that point, that degree of that introduced a huge amount of flexibility into the whole rendering process. So today, GPUs can execute any program you can write. All of the elements of the original pipeline are still there, but they're all reconfigurable in ways that, the GPU is a full general purpose computer, a full general purpose processor. Not very different. Well, not unlike in capabilities your CPU. There's differences, and we'll talk about them next. But yeah, GPUs they've evolved from basically from these fixed function pipelines to these fully programmable stream processors. So stream processor is an interesting term. I think people applied it to this pipeline because you have these data elements that move through the pipeline, and as the data elements move through the pipeline, each element doesn't affect the other elements, and each pipeline stage can execute asynchronously, like they're not affecting one another. I think that's where the stream comes from. The data streams through the pipeline. But if you look at how they work, stream processor I don't think is a very good name at all. There are some hardware efficiencies to be had because of their stream nature, but I think a better name for them is shotgun processors. Why is that? Here's a high-speed photograph of a shotgun seen from the side. And as you can see, it's got a whole bunch of balls of shot. They're all going in the same direction, more or less, and they're not spreading out very much. And they're all doing the same thing. They all came from the same place. They're all going to the same place. So you have so those are executing together, and that is what the shotgun blast did to some poor guy's mailbox. So as you can see here, the effect is it's clustered. So this property of this clustered effect is really great for rasterization, because in rasterization you're working with one part of the you're working with a bunch of triangles that are all near one another. They're rasterized into fragments that are in pixels that are adjacent to one another, and those and then you get everything performs very well with that. So let's be a little bit more civilized. Instead of blowing a hole and blasting a hole in his mailbox, let's paint a teapot on it. So that's much better. As you can see, every part of the teapot is close by some other part of the teapot. So in this case, the shotgun processor for drawing a teapot is our friend. Here's the architecture diagram of the PowerVR GPU. I mean, it's vastly simplified, but you get the point. the processor, the unified shading cluster array, is the biggest part of this GPU design. Everything else, the stuff that feeds the unified shading cluster array, is pretty small. Is pretty small by comparison. That's so here's another company's GPU. You can get a hint as to which company by the color coding. This is a die photograph of their GPU. And this here, everything that I've covered up all the parts of the GPU that are not that stream processor. So you can see the vast majority of this logic is there to do math. This thing is a beast. This thing is capable of many trillions of mathematical operations per second. And what you have here, I mean, this is mostly high density math that you're seeing. So very little area is spent on everything else. This is a CPU. This is about the same era as that GPU, about a year old, or 2 years old. Let's look at the same view of that. That's the math part. Everything else, what I didn't cover up, is the math part of the CPU. Everything else on there is other logic to support that, to keep it fed, to keep the data nearby so that it doesn't have to waste time going out to, waste time going out to memory, so that it can run at a higher clock frequency. So it can do things like speculative execution to maintain higher clock frequencies. This, so why is that? Why is so much more of the area of a GPU dedicated to math versus a CPU? Are CPU designers just dummies? No, clearly they're not. CPUs are latency optimized. So as a result, they're relatively good at handling just about every type of compute problem. GPUs are throughput optimized, meaning they're insanely good at handling a subset of compute problems that lend themselves to this data parallel approach, where the data is nicely arranged in memory, and you don't have to worry about a lot of branching, control flow branching, which is where a program might do one thing or it might do something else. You don't have to worry about bad data locality, where you need to pull random bits of data out of memory. So CPUs have all that extra support infrastructure in order to maintain good efficiency at doing what they need to do, which is to run pretty much all the software, all the apps that are out there. GPUs, a lot less flexible. So ray tracing is an interesting problem here, back to ray tracing, because it should be one of these perfectly parallel problems. In fact, it's been described as an embarrassingly parallel problem, which means that one ray, in this case, doesn't interfere with another ray at all. So it should be perfect for a GPU, but it isn't. And the reason it isn't is because, unlike the shotgun computer, where everything, when we painted that teapot on the mailbox, everything, the only thing we messed with were the pixels that were the teapot. But in ray tracing, we don't have that luxury. Here is a sculpture, and this is in the lobby of the CNET building up in San Francisco, the CBS Online building now. It's a bit strange, abstract, but it makes a good point. Here I am in the orange shirt, and you can see that by adding me to the picture, you've had to modify pixels all over the place. You have I'm here, I'm there, there. I think I counted it. It's a little under a dozen different places I show up in there, and that doesn't even take into account the fact that I throw a shadow on the floor, then that shadow has a reflection. The point is, in the real world, in the real world, light bounces, it scatters, it bounces off everything, it scatters everywhere, and you can't have this simplistic approach to rendering 3D. So, as you can see, that sculpture was a bit abstract, but the phenomenon is very real. So here's a slightly less contrived, but still contrived example. You've got light bouncing off those cups, hitting the aluminum laptop, and finding its way to the camera. This is how real light behaves. This is how real life behaves. Without these details, your image will not get across the Uncanny Valley. You'll have that scary, terrifying woman that I showed you a couple slides ago. How do we do ray tracing efficiently? Well, here's the diagram of Power VR again. We've added these blocks here. Basically this Coherency Engine. We've invented this Coherency Engine is a massively parallel queuing machine. So what it does is it maintains thousands and thousands of queues, and each ray lives in one or more of these queues. And as the rays move through the scene, they get queued up to load different parts of the scene from memory, and to execute different pieces of shading code, depending on what that is. So then the output of these queues get fed back around to the unified shading cluster, meaning that this shotgun computer now can execute at perfect efficiency, because it's now given big enough batches of work to function within its operating parameters that it was designed to operate in. So yeah, you can see the rays as they move through, as they're moving through the scene, they're getting put into different queues, then those queues are processed, and then the rays can be assigned into still different queues until ultimately you have an image that comes out the other end. So what that effectively means is that all the rays that find its way to my orange shirt can be tested together and can be shaded together and processed together. So you have the shot. So in spite of the fact that they're going all over the place, they're still within the efficiency point of efficiency sweet spot of the GPU architecture. So now here's the fun part. These are some of the images. So this is an example of an image that would be impossible to do any other way except ray tracing. What we have here, we have a mathematical model of the behavior of the way light interacts with the glass. We compute the Fresnel term based on the angle that the light hits the glass, and then with that Fresnel term, we can figure out how much of the energy passes through the glass, how much of the energy reflects off the glass, and we can render really cool surrealistic images like this one. Here's another example that we like. This one wasn't. It's with the interactions between the water and the boat, it's pretty. I could probably fool you into thinking this was a photograph, but it isn't. So we think that this technology is a key enabler that's going to allow interactive content to look as good as movies. And we think that perhaps with other technologies that are coming along, interactive content may someday end up in a place where it'll be indistinguishable from reality, and that's a big claim. But there's other technologies that are needed to make that whole puzzle come together. But we think ray tracing sits at the center as a key enabler. I particularly like this one, because this one shows how ray tracing can interact with photographs as well. The car, that's totally computer generated. The background, that began as a photo. I mean, we put there was a black and white filter applied to it, but other than that, a photograph. So we think ray tracing opens up opportunities for all kinds of, other use cases like augmented reality. In fact, we think there's a lot of use cases for ray tracing. Yes, ray tracing is great at rendering photorealistic imagery, but we also think that it has use cases well beyond that. Ray tracing can be combined with traditional rasterization, so it's not an all or nothing proposition. With this bit of hardware that we're adding to the GPU, we think that it can be applied to other algorithms just to make the GPU run more efficiently generally at parallel tree traversal problems. We think even beyond graphics, we think ray tracing, remember, ray tracing is just the fundamental ability to test line segments against a 3D representation of a scene. So a scene's in a virtual 3D database. So we think physics is a great example of that. We've done particle simulations using the ray tracing hardware. Fluid propagation stuff. We've done collision detection. We've accelerated collision detection using this same hardware. We're looking at doing acoustic propagation. Figuring out how to simulate echoes by using the line segments as the paths that the sound is going to propagate. It's not it doesn't quite model things like diffraction, but it gets you pretty darn close. You can model sympathetic resonance and come up with more accurate acoustic models than can be done without it through other state-of-the-art techniques to model acoustics. Multi-perspective rendering. Ray tracing is vastly more efficient than rasterization as soon as you start to consider multiple perspectives. We were working with a company at one point to create holograms to render holograms, because in holograms you're basically rendering an entire light field. So you have in their case you had 60,000 different perspectives that you could view the scene from. We had to render all of them. Ray tracing pulls way out ahead of rasterization when you start rendering many perspectives. So I just want to say in closing, ray tracing is a low-level technique. When the first microprocessors were built, their target customer was a calculator. And it turns out that the ability to do math really quickly it has a lot more implication on our lives today than calculators. I don't know. I'm not claiming that that what we've built is going to be as big a deal as a microprocessor. But what I am saying is that it's a low-level capability that's going to have applications that are impossible to foresee from where we're sitting now. But I can promise you this: those applications will go well beyond video games that look like movies. Thank you.
So now we are open for questions. If you have a question, please line up at the microphone set up there. So let me first ask, please, choose using the microphone. So let me ask the first question. We know some people try to support the ray tracing technology with hardware, right? And before we always run this with the software. But how much different, speed difference or price difference we are talking about?
Right. Okay. So we, you hit the nail on the head, because we talk in terms of efficiency, not in terms of speed, because they're really two sides of the same coin. You can scale something up and make it faster, or you can take something that today requires a workstation and put it into a phone. With the architectural changes we've made, we've seen about 100x efficiency improvement running ray tracing.
100 times.
100 times, yes, that's right.
Is it necessary to...
your company, your name, and the question.
Working high-performance computing for music production. My name is Antonio Carvalho, and my question is there technology necessary to live inside the GPU, or it can be somewhere else?
Well, ray tracing as an algorithm can live anywhere. the ray tracing acceleration hardware we built is definitely part of the GPU. It's all about scheduling with the GPU's inner workings to get that efficiency.
So if my understanding is correct, what you're doing is getting the GPU one step closer to being a CPU.
You could think of it that way. I guess it's a rose by any other name. It's still different. The GPU is still a massive SIMD machine, single instruction, multiple data, which means you have a lot of different processing elements that are doing the same thing on multiple data elements. We're not changing that because that is one of the things that makes the GPU so dense at math, so efficient at doing math, and we're not changing that. But what we're doing is we're doing some scheduling at the front of the pipeline to allow GPUs to remain efficient, where right now they kind of fall down because of memory load latencies and because of control flow divergence and some of the other things that cause GPUs not to be good at ray tracing.
My name is Mohan. I'm from Imagination Technologies also.
So same company.
Yeah. So do you see applications of ray tracing for doing the reverse of what you're doing? Like, instead of rendering the image, do you have to find out what are the various light sources in the room? Is that possible with this technology? Or?
That is a very hard problem. There's a lot of research going on. Not exactly sure what I can talk about, what's public and what isn't. I'm sure that there's research at all sorts of companies. I only know the research that I'm involved with. Yeah, it's okay. Ray tracing per se isn't necessarily the right algorithm for that. However, the coherency engine is really good at basically the coherency engine makes the GPU into a massively parallel tree traversal machine, and a lot of vision algorithms do involve tree traversals. So I could definitely see this hardware technology being applicable to a lot of vision algorithms. But yeah, working back to finding the light sources it takes some guesswork. I've seen public papers in which people are really good at backing into light sources if you know the material properties, really good at working out the materials if you know the light source positions. It's really hard to figure out both. But our brains do it all the time, so it's definitely an open area of research.
Thank you.
So let me ask one more question. That some people say that they would like to have a GPU which support a smartphone, support ray tracing. I think that's probably a dumb question because 10 years ago some people say that phone don't need a GPU, and right now we prove it's wrong. But I still want to say, is that make sense? Is that get any benefit from adding the ray tracing engine in that kind of CPU?
Yeah, we think mobile GPUs are the most important GPUs, obviously, but not just because we make a lot of them. You can do a lot of things.
But a very small screen, right?
Small screen, yes, but you also have cameras on that device. The mobile form factor lets you do things that you might have a harder time doing on a desktop machine. Like, for example, with the camera and the accelerometer, you can walk around and take capture the room that you're in, and then with ray tracing, be able to incorporate that content into applications that you wouldn't be able to do on a desktop because you couldn't capture the world on the same device. So, like I was saying earlier, the use case stuff is really a wide open frontier now. But we think mobile phones and tablets and other devices are frankly the best opportunities for this technology. We think desktop GPUs are, well, we don't make any desktop GPUs.
Okay, so we would like to thank Lucas' great presentation and slides. His slide will be available after the talk. That's thank you. So on behalf of CIE, I would like to present a small token to Luke.
Thank you very much.